Hi students, we are introducing the most expected questions from the coordination chemistry for your CBSE Board Exam 2025. Based on deep analysis of trends and previous year papers, we are bringing you the most important, most probable 15 questions which are expected to come for the 2025 CBSE Board Exam. What is meant by chelate effect? Give an example. Okay, first I will give you a detailed answer, then a statement answer. For explaining chelate rings, see we can check these two coordination compounds. Here you can see En is the ligand, which means ethane 1,2-diamine is the ligand, and here you can see NS3 is the ligand. What is the basic difference between these two ligands? This one is bidentate, which means it can simultaneously make two bonds with the central metal ion. Now here you can see NS3, right, which is a monodentate. You can see only one bond, right? Now, due to the bidentate character of En, it is actually forming a ring structure, right? You can see a ring structure. We call it as chelate rings. Okay, now these chelate rings are more difficult to break than the single bond here formed by monodentate ligands. Definitely leads to what? Higher kinetic and thermodynamic stability of chelate ring compounds. Here is your statement answer. The chelate effect refers to the enhanced stability of a coordination compound that contains a multidentate ligand compared to one with similar monodentate ligands. This occurs because multidentate ligands, also known as chelating ligands, form multiple bonds with the central metal ion, creating a ring-like structure. This chelating rings reduces the possibility of the ligand dissociation, making the complex more stable. This is one of the most important questions of this lesson. Why CO is a strong ligand? Okay, first I will give you a detailed answer, then a statement answer. There are two reasons which make CO group a strong ligand. Reason number one, see, CO is a good electron donor. CO has a lone pair of electron on the carbon atom, which it donates to the metal ion. Definitely what happened? It will create a strong sigma bond between CO group and the metal ion, right? That is similar to all other ligand metal ion relation. Correct? But in addition to that, CO is establishing one more bond with the metal ion due to back bonding. CO has empty orbitals which can accept electrons from the metal ion. So what will happen? Metal ion will donate its electrons to the CO group, which will create a second bond between metal and CO group. Hope you understand. These two effects, donation and back donation, together make the bond between CO and the metal very stable. Okay, that is why CO group is considered as a strong ligand. Hope you understand. This is your statement answer. See, there are two reasons basically. Sigma bonding, first one, electron donation of CO. In CO, the carbon atom has a lone pair of electrons. This pair is donated to the central metal atom through sigma bond. Now second is pi back bond. CO also has empty pi star orbitals that can accept electrons from the metal's d orbitals. This is called pi back bonding. It strengthens the bond further by creating a double interaction between the metal and the CO ligand. Third one is synergic effect. That is the combination of sigma donation and pi back bonding, called a synergic effect, make the bond between the metal and CO very strong, stabilizing the complex. The CFSE, crystal field splitting energy for octahedral, COCl6 is C18000, and you are supposed to find the crystal field splitting energy of this particular complex, right? COCl for 2-. Okay, we can check. All of you already know, right? There is a relation between octahedral and tetrahedral CFSE. What is the relation? This one, right? CFSE of tetrahedral is equal to 4 by 9 of CFSE of octahedral, which is given in the question. What is that? You can see 18,000, right? So what is that? 4 by 9 into 18,000. You can calculate it and you will be getting the answer like 8,000. Hope you understand. CuSO4 dot 5H2O means copper sulfate pentahydrate is blue in color, while copper sulfate is what? Colorless. Why? First I will give you a detailed answer, then a statement answer. If you check the first compound, you can see the central metal ion, right? Cu2 plus, correct? Also you can see ligands, right? Correct? Now in the presence of ligands, what happened to the central metal ion? We know the degeneracy of the d orbital will lose, correct? As a result, you will be getting a set of new 2 orbitals, correct? Now, if unpaired electron is present, then what will happen? Electron will absorb light energy and excite to the higher energy level. You remember, right? See, when ligands approach the central metal ion, the degeneracy of the d orbital of the central metal ion will be lost. As a result, what you will get? You will be getting a set of new 2 orbitals like this. Now, if unpaired electron is present, it will absorb light energy and excite to the higher set of orbitals, correct, right? We call it as DD transition. So for a coordination compound to be colored, you have to check presence of ligands are there or not. Here you can see ligand is present, correct? So definitely what happened? CFT, crystal field splitting happens. Then you have to check unpaired electron is there or not. Of course, Cu2 plus have unpaired electron. So definitely what will happen? That compound will have color due to the DD transition. You understand? In the hydrated form, water molecule act as ligand and surround the Cu2 plus ion. These water molecules split the d orbitals of Cu2 plus, allowing what? DD transition of electrons. Hope you understand. This absorption causes the compound to appear as blue color. Regarding copper sulfate, there is no water molecule, right? No ligand, no crystal field splitting, no DD transition, so no color. Okay, now you can check the statement answer. In copper sulfate, okay, copper sulfate pentahydrate, water acts as ligand. As a result, it causes crystal field splitting. Hence, DD transition is possible in copper sulfate pentahydrate and shows color. In the anhydrous copper sulfate, which means there is no water, due to the absence of water ligand, crystal field splitting is not possible and hence no color. Hope you understand. How many ions are produced from this particular complex compound in solution? That is the question. See, it's very easy, okay? What you have to do? See, count the coordination entity as a single ion. So 1. Now check how many counter ions are there. 3. Add it. 1 plus 3, 4. So how many ions are produced? 4 ions are produced. See, for coordination entity, okay, the components inside the coordination entity does not undergo further dissociation. Remember it, okay? So here 1 and here 3 counter ions, total 3 plus 1 is 4. When 1 mole of CrCl3.6H2O is treated with excess of AgNO3, 3 mole of AgCl are obtained. You have to find the formula of the complex, right? It's a very easy question actually. See, what we are adding AgNO3. And what we are getting? 3 mole of AgCl, which means this particular compound contains 3 ionizable chlorine or 3 ionizable chloride ion. Correct? Now you check the compound. How many chlorine is there? You can see 3 chlorine, right? And all that 3 chlorine are ionizable. Ionizable means what? They are outside the coordination entity. The chlorine, okay, all 3 chlorine are outside the coordination entity. They are ionizable. That is why you are getting AgCl. Hope you understand. Now what is left? You have chromium, the central metal, and see what is remaining. You have water molecules, right? They will be acting as ligand. Hope you understand. Which complex compound is most stable? See, they have given 4 options, and if you check all that 4 options, okay, have same central metal ion. Now, if you check the ligands, okay, most of the ligands are monodendrite ligands. See, NH3 you can see NO3, Cl2, NH3, NH3, H2O, Br. But except En, right? En is what? En is bidentate. Now what is the specialty of bidentate? It can form chelate rings, right? Not like monodendrite. It is actually making 2 bonds with the central metal ion, almost like a ring, correct? And these chelate rings are very difficult to break than the single bond formed by the monodendrite. So definitely that will be thermodynamically and kinetically more stable. So we know if a chelate ring is there in a complex compound, that compound will be always more stable. Remember this question. There are high possibility, okay, for your exam. Why are low spin tetrahedral complexes not formed? First I will give you a detailed answer, then a statement answer. For answering this question, you must know this criteria. Delta T, crystal field splitting energy, greater than pairing energy. Then pairing will take place. Okay, then pairing will take place. And the spin will be what? Low spin. Now, if pairing energy is greater than delta T, then pairing will not take place. Okay, no pairing. And what is the spin? It will be high spin. See, this is the criteria you have to remember. Okay, now we can check the tetrahedral complex. Okay, now see 1, 2, 3, 4, 5 ligands are approaching, right? So it become what? 2 sets of orbitals like this. Correct, right? Okay. Now see, this is the energy difference, right? Delta T. For tetrahedral, delta T is very small. Delta T is very small, smaller than pairing energy. So no pairing, high spin. Hope you understand what I am saying. Okay, so assume you have 4 electrons here. So first electron here, second, third, not here. Okay, if it is here, this pairing, right? Not going for pairing. Third one, fourth one, like this. Hope you understand. So here delta T is very small and never exceed what? Pairing energy. So no pairing take place. It will be always what? High spin. Why are low spin tetrahedral complexes not formed? Hope you understand the answer. On the basis of CFT, explain cobalt-3 forms a paramagnetic octahedral complex with weak ligand, whereas it forms a diamagnetic octahedral complex with strong ligand. Which means, see, the central metal is CO3 plus. Now, if weak ligand is approaching, what we are getting? A paramagnetic octahedral complex. Now, if a strong ligand is approaching, what are you getting? A diamagnetic octahedral complex. Okay, we are supposed to prove it. Okay, okay, let us see. See, we know atomic number of cobalt is what? 27, right? Which means what is the configuration? Configuration will be 4s2 3d7, right? Now cobalt 3 plus means what? Cobalt 3 plus means configuration will be 4s0 3d6, correct? Now we have d orbitals, 1 2 3 4 5 orbitals, right? How many electrons? We have 6 electrons, 1 2 3 4 5 6. Okay, here also cobalt 3 plus only, right? Cobalt 3 plus only. This is about weak ligand and this is about strong ligand. Okay, so same configuration, so I am not rewriting it again. So 1 2 3 4 5 6. Okay, now when ligands approach, okay, here weak ligand, you know, for weak ligand this energy gap will be very less. Okay, which means delta O will be lesser than pairing energy. Delta O will be lesser because it is weak ligand. Now here strong ligand, right? Strong ligand means what? Delta O, which means the energy gap. Okay, energy gap here 1, 2, 3, and here this one, right? This is the energy gap. Delta O will be very big. Delta O greater than pairing energy. Hope you understand. Okay, here pairing energy is bigger. Okay, delta O is lesser. Why? Weak ligand. This gap is lesser. Okay, if pairing energy is greater, pairing will not take place. So how to write it? 1, 2, 3. Pairing energy is greater, pairing will not take place. How many electrons we have? 6. 1, 2, 3, 4, 5, 6. Okay, here pairing energy is lesser, so pairing will take place. How many electrons? 6, right? 1, 2, 3, 4, 5, 6. Hope you understand. Now here you can see what? Unpaired electron, right? So it is paramagnetic. Okay, here what you can see? Complete paired electrons, so it is diamagnetic. Hope you understand. The color of the coordination compounds depends on the crystal field splitting. We already know, right? What will be the correct order of absorption of wavelength of light in the visible region for the complexes? They have given 3 complexes. See, for answering this, first of all, you must know what? See, a d orbital, degenerate d orbitals, right? A state of same energy, all of them have same energy. When ligands approach, what will happen? See, it will split into 2 sets, right? Like this. Correct? Now this energy gap, okay, it is octahedral complex, we can say delta O. The energy gap is delta O, right? Now this delta O depends on what? The strength of the ligand. If the ligand is more stronger, delta O will be greater. That's what I'm saying, right? Then for DD transition, see, you know, the color of the coordination compound is due to the DD transition of unpaired electron from lower T2G to higher EG. Correct, right? If the ligand is stronger, this gap will be more. Then electrons are supposed to gain more energy, right? Then only it can shift from T2G to EG. You understand what I'm saying? Correct. Okay, so if ligand is stronger, delta O will be greater. If delta O is greater, then electrons need more energy for the shifting process. Then only it will get colored, right? Hope you understand. So, if strength of the ligand is more, then energy of light absorbed by the electron must be more. Correct, right? Now you know energy is equal to what? Hc by lambda, which means energy and lambda are inversely proportional, right? Which means energy inversely proportional to lambda. For a ligand with higher strength, energy must be greater. So what about wavelength? Wavelength must be lesser. Hope you understand what I am saying. Now you check the order. Which one is the, see, I am saying this one is A, this one is B, this one is C. Now which ligand is maximum stronger? Cn, right? Cn minus. Then which one? Then NS3, right? Sorry, NS3, right? Then which one? H2O. Okay. So B, okay. B contains Cn. That is the strongest ligand. Maximum energy. Wavelength will be least. Hope you understand what I am saying. So B means this one, okay. This one absorb light of least wavelength. Then which one? C, then NS3, right? NS3, this one, A. Then which one? C. Hope you understand. C is the weakest ligand. If the ligand is weaker, strength is less, energy will be less. If energy is less, wavelength will be more. Hope you understand what I am saying. What is the oxidation state of central atom of NiCO4, right? See, it's very easy question. You are supposed to find the oxidation state of nickel. Okay, you have carbonyl group, right? Carbonyl group, you already know the oxidation number is 0, correct? So it's a very easy question. Totally it is neutral. So x plus 4 times 0 is 0. So what is that? X is equal to 0. So oxidation state of nickel is 0. Hope you understand what I am saying. A coordination compound CrCl3.4H2O precipitates silver chloride when treated with silver nitrate. So we are adding silver nitrate to this complex compound so that silver chloride is precipitated. Chloride is precipitated, right? Which means one of the chlorine in the coordination compound is ionizable. Which means one of the chlorine is 100% outside the coordination entity. At least one of the. Like at least one of the. Okay, we don't know the number. Now the molar conductance of its solution correspond to a total of only 2 ions. Only 2 ions means one is what? One is our coordination entity and other one will be definitely what? One chlorine. Correct, right? Only 2. If it was 3 ion, you will be having 2 chlorine outside and rest will be inside the coordination entity. So what is inside? Cr. You have 4H2O, right? Then what? Cl2. Total 3, 1 outside and 2 inside. So Cr, H2O4, Cl2, outside you have Cl. Hope you understand. Now how to name it? For naming this, first of all you must know the oxidation state, right? Oxidation state. X, H2O is 0, chlorine is -1, this chlorine is also -1. On calculating you will be getting what? X is equal to 3. Now how to name? See, tetraaqua, dichlorido, correct? Chromium. Then what? Inside Roman letter 3. Then chloride. Tetraaqua, dichlorido, chromium, 3, chloride. Hope you understand. Arrange the following complexes in the increasing order of conductivity of their solution. Okay, they have given 1, 2, 3, 4 complexes. How to answer this? It's very easy. More the number of ions, more will be the conductivity. See, if you check, you can see. Here you can see only one particle, right? Only coordination entity and it is not charged. Okay, here you can see coordination entity is there, counter ion is there, 2 ions. Correct? Now here if you check coordination entity and 3 counter ion, 2 plus 1, what is that? Sorry, 3 plus 1, what is that? 4. 3 plus 1, okay, 4. Here 1 plus 1, 2. And here what you can see? 2 counter ion plus coordination entity. So what is that? Total 3. So if you are giving like name A, B, C and D, which one have maximum ions? C, right? So C, maximum number of ions, maximum conductivity. Then you can see D, right? This one. It have 3 ions. Then you can see here 2 ions, right? It is B. Then which one? Here you can see only coordination entity and it does not have a charge. Okay, least conductivity. Okay, more the number of ions, more will be the conductivity. That is a key, okay, for this question. Differences between double salt and complex compounds. Okay, it's a theory question. We can check. A double salt is a compound that dissociates completely into its constituent ions in water and loses its chemical identity. It is stable only in the solid state. So you have an example more salt. So you can see FeSO4, you can see FeSO4, NH4 twice SO4, 6H2O is more salt. But what happens if you dissociate, if you mix it with water, it completely dissociates to ions like this, so that it will lose its chemical identity. Hope you understand. But if you check complex compound, a complex compound is a compound in which a central metal ion or atom which is surrounded by ligand forming a complex ion, which means coordination entity that does not dissociate completely in water, okay, and retain its identity. Hope you understand. See a complex compound, if you check a complex compound, see dissociation of the components of the coordination entity is not taking place. Meanwhile, what happened to double salt? Double salt dissociates completely and loses its chemical identity. Remember one important thing. See this example. Okay, this example, more salt. Sometime in exam they will ask to write the formula of more salt. It is the textbook. So just go through that. Why are different colors observed in octahedral and tetrahedral complexes for the same metal and same ligand? See, metal is same, ligand is same, but colors are different for octahedral and tetrahedral complexes. See, it's very easy. See, if you take octahedral complex, okay, 6 ligands are approaching, so you will be seeing a CFT diagram like this, and this is delta O, right? Correct. Now, if you are doing the same for a tetrahedral complex, what you can see? See, here you can see 2, here you can see 3, and this is delta T, and delta T is very small compared to delta O. Correct. Now, if unpaired electron is present, what will happen? It will absorb light and undergo what? DD transition. This is how the compounds are getting color, right? And remember, the absorption of the light by the unpaired electron depends on this energy gap. Correct, right? Okay, now delta O is greater than delta T. Correct, right? Which means the electron here absorb more energy. Correct? If energy is more, what is the meaning of that? Energy is equal to Hc by lambda. Correct? If energy is more, it is absorbing a light of smaller wavelength. Now here for tetrahedral, again E inversely proportional to lambda. Here energy is less, right? Energy is less means the electron here is absorbing a light of what? Of higher wavelength. If wavelength is different, color will be different. Hope you understand what I am saying. And the compounds will be in which color? In the complementary color, not in the color which is absorbed, in the complementary color. Anyhow, they are absorbing colors of different wavelength, and they will be seen as what? In the complementary color. If the colors are different, the complementary color will be also different. Hope you understand. Here is your statement answer. The color of a coordination complex compound depends on the wavelength of light absorbed, which correspond to the energy gap between the split d orbitals. Since delta T is smaller than delta O, tetrahedral complexes absorb light of longer wavelength, which means lower energy, compared to octahedral complexes, which absorb light of shorter wavelength, which means higher energy. The difference in the absorbed light leads to different colors being observed. Hope you understand. These are our predictions on coordination chemistry for CBSE Board Exam 2025. Okay, all the best to all my dear students.